As I told, we shall continue in this lecture with our current project, namely exploring various convergence theorems in Lebesgue integration theory. And we already stated and proved in detail one such convergence theorem, namely monotone convergence theorem. We shall recall the theorem, and today's lecture will start by supplementing a few remarks to the monotone convergence theorem. So first, let us recall the statement of monotone convergence theorem. As the name suggests, you are having a sequence of measurable functions that are monotone. Once it is monotone, to be precise, monotonically increasing, it will converge to some function, and integral of that limit function is same as limit of the integrals. If sequence Fn, n element of n, is a sequence of non-negative extended real valued measurable functions such that 1. Fn less than or equal to Fn plus 1 for all n. That is, Fn of x is less than or equal to Fn plus 1 of x for all n and for each fixed x in the domain. Let us take domain to be entire real number system. The condition 1 will automatically imply that Fn converges. Just to make a notation, we call the sum or the limit to be f of x. F of x is equal to limit n tending to infinity Fn of x. Let me repeat the fact that convergence is not an assumption. It is automatic from 1. Once it converges, it will, the limit you can talk about. I want a notation for the limit, and hence I am introducing f of x is equal to limit n tending to infinity Fn x. Then the theorem guarantees that integral f dm is equal to limit n tending to infinity integral Fn dm, integral over R. In fact, you can take the domains of function Fn to be some measurable set in R, let us say E in R, and you can state the result in terms of integral over E. So this is the statement we made and we proved in it in detail. Now let us make a few remarks on this theorem. The first remark is as follows. If you see the assumptions in monotone convergence theorem, one is that it is monotonic for each x in the domain. Okay. And because of that, you can talk about the limit, and hence you are talking about point-wise convergence for each x in the domain. Please keep in mind that Lebesgue integration to some sense is defined only up to almost everywhere functions. What I mean is the following. If you have two functions f and g, and F and G are not equal everywhere, but they are equal almost everywhere, then also integral of F will coincide with integral of G. Do you agree?
Yes, sir.
Yes.
For integral to coincide, you don't want the function to be equal everywhere in the domain. It is enough to have functions to be equal almost everywhere in the domain. And if you see, finally, the theorem talks about the equality of integrals, roughly. So an automatic question is, can we have the theorem with the hypothesis changed to almost everywhere instead of working with everywhere? For instance, you assumed that Fn less than or equal to Fn plus 1 for all n. That means Fn of x is less than or equal to Fn plus 1 of x for all x in the domain. Instead of having all x in the domain, suppose you have almost everywhere. Similarly, suppose the limit, point-wise limit, exists for almost everywhere. Then can we say integral of f dm is equal to limit of integral of f and dm? That's the question we want to address now. Okay. So let me put it as a remark. To put in simple language, the hypothesis in the monotone convergence theorem, we are changing to almost everywhere from everywhere in the domain. In LMCT, Lebesgue monotone convergence theorem, we assumed Fn of x is less than or equal to Fn plus 1 of x for all n and for each x in R or in the domain E subset of R. A natural question is, can we replace everywhere with almost everywhere? What is your guess? Yes or no? I have already given you a hint. Integral remains unaltered if the functions are equal almost everywhere. So what is your guess with that in mind?
Yes, sir.
Yes means answer is yes, right?
Yes, sir.
Yes.
Okay. So now let us state the theorem. Which is again called monotone convergence theorem, with a weaker hypothesis. Let Fn be a sequence of extended real valued non-negative functions. Non-negative functions. That is, Fn's are from R to closed interval 0 infinity. Such that Fn less than or equal to Fn plus 1 for all n in n almost everywhere. Meaning Fn of x is less than or equal to Fn plus 1 of x, not for all x in the domain, but for almost everywhere in the domain. Then sequence Fn converges almost everywhere to a measurable function. Let us call that function to be f, and integral f dm is equal to limit n tending to infinity integral fn dm. With this assumption, Lebesgue integration is stable with respect to taking limits. In other words, you can interchange integration and limit. Please understand the difference in the hypothesis. In the original theorem, we assumed that fn of x is less than or equal to fn plus 1 of x for all x. Here we are assuming that fn of x is less than or equal to fn plus 1 of x almost everywhere. Okay. Now keep the definition of almost everywhere in mind. Some property holds almost everywhere means the set on which that property does not hold is of measure 0. Okay. Now, without further delay, let us go for the proof. The central idea of the proof is to convert the problem to everywhere. That is, we shall use the monotone convergence theorem, which we stated and proved already. Okay. For that, I have to consider those points at which fn of x is less than or equal to fn plus 1 of x. Okay. To do that, let me consider the following set. Let us look at, let us say, A, collection of all x in the domain for which fn of x is less than or equal to fn plus 1 of x for all n. So we are bothered about only those x for which the function sequence of functions is monotonic increasing. And this A I could write as intersection of all ans. You can guess what is A, where an is for a fixed n, an is collection of all x such that fn of x is less than or equal to fn plus 1 of x. Is that okay?
Yes, sir.
Now, what is our assumption? Fn is less than or equal to fn plus 1 almost everywhere. By the assumption, for each fixed n, or each fixed n in n, fn is less than or equal to fn plus 1 almost everywhere. That is, fn of x is less than or equal to fn plus 1 of x almost everywhere. Now, what is the meaning? This property holds almost everywhere means the set on which this does not hold is of measure 0. In terms of the sets that we introduce, that means that measure of an complement is 0. Do you agree?
Yes, sir.
Therefore, measure of outer measure or measure doesn't matter. An complement is 0. Why it doesn't matter? Because once outer measure is 0, the set is measurable. So that you can talk about measure. Okay. And once a complement of a set is measurable, each set is set is measurable. So ans are measurable. Thus, I will write m star. Ans are measurable and measure of an complement is equal to 0. Okay. Now let us worry about measure of a complement. Therefore, measure of a complement is equal to measure of, and once ANs are measurable, A is measurable. And therefore A complement is measurable. So I can talk about measure of A complement, not just Lebesgue countermeasure. I can in fact talk about the measure. Measure of union n is equal to 1 to infinity AN complement. Okay. And now countable subadditivity. This is less than or equal to summation n is equal to 1 to infinity measure of AN complement. And measure of AN complements are 0. Okay. So you have measure of A complement is 0. Now consider, you know that once Fn is increasing, it has a limit function f of x. Okay. But here Fn is not increasing everywhere, it is increasing only almost everywhere. Okay. For instance, Fn is increasing everywhere on A. Do you agree? Fn is increasing everywhere on A. Is
Yes,
that
sir.
okay?
Yes, sir.
Yes. Therefore, on A, the sequence Fn will have a limit.
Yes, sir.
That I am calling as G. Consider G of x is equal to limit n tending to infinity Fn x. For all x in not the domain of Fn's, maybe R or E, but on A. On A, I can talk about the limit for all x. Okay. Now we are exactly in a position to apply monotone convergence theorem because Fn's are increasing everywhere on A and Fn has limit G on A. So on A you can apply Lebesgue monotone convergence theorem, which we proved already. Okay. But before that, note that G is measurable because Fn's are measurable. Okay. And let us define and not define, let us consider f of x is equal to g of x for every x in A and 0 for every x in A complement. Okay. And do you see that f is equal to g almost everywhere?
Yes, sir.
Because where it is not equal, maybe is only on A complement at the maximum, and A complement is of measure 0. Okay. Therefore, f is equal to g almost everywhere on R, on the entire domain. And you know g is measurable. Therefore, f is measurable. Therefore, f is measurable. Okay. Now, integral f dm. I am talking about integral over the entire domain. Okay, is equal to this. We have proved domain decomposition property. Integral over a f dm plus integral over a complement f dm. Okay. And on a f and g are same. So integral over a g dm plus on a complement f is 0, and therefore this will not contribute anything. Therefore, this is equal to integral over a g dm. Integral over R or the domain of f. No. What is integral over f and dm? I mean integral over R f and dm is equal to integral over a f and dm plus integral over a complement f and dm. I am reducing the problem to on A because on A everything works everywhere, not almost everywhere. And that is equal to integral over A f and dm. Okay. Why on A complement f and dm, integral f and dm will be 0? y on a complement, integral fn dm will be 0. What I'm saying is plus 0. This will be 0. 0. And therefore equal to integral over a fn dm. Can you find out the reason? Do you know that fn's are non-negative?
Yes, sir.
Therefore, how do you define integral of fn via integral of simple functions? Right?
Yes,
And
sir.
now you want integral of simple functions on a complement. But what is the measure of a complement?
0.
0. And how do you define integral of simple function? Summation of values taken times measure of the sets on which those values are taken. Measure of a complement itself is 0. Therefore, integral of those simple functions will be 0. And therefore, integral of f and dm's will be 0. Are you okay?
Yes.
Yes.
Yeah. So we have this. Okay. Now, since fn is less than or equal to fn plus 1 on a, this is for all x on a, and limit n tending to infinity fn of x is equal to g of x, we can apply. This is a perfect situation where we can use monotone convergence theorem. By monotone convergence theorem, which we proved previously, what you can say is integral over g dm is equal to limit integral of fn dm. Everything over a. Okay. Therefore, integral over r f dm, which you observe that this is same as integral over a g dm, that you have observed. Okay. And that is equal to limit integral over a f and dm by monotone convergence theorem. Just now we wrote. That is equal to, and integral over a f and dm is same as integral over r f and dm. So this is equal to limit integral over r f and dm, which proves the result. Integral of the limit is equal to limit of the integral, even when the limit you can talk only almost everywhere, and the hypothesis of monotonicity is available almost everywhere. Okay, so this is the best statement or the best way to put Lebesgue monotone convergence theorem. Are you okay with it?
Yes.
Yeah.
Yes, sir.
Yes.
So this finishes the monotone convergence theorem, and one remark on it. Let me put one more remark. If you see the statement closely, we use monotonically increasing sequence. So an obvious question is, can we have the statement or the result, for instance? Statement definitely you can have. The question is whether the result hold for monotonically decreasing sequence. Okay, so let me put it as a remark. If fn is a sequence of non-negative extended real valued measurable function such that fn greater than or equal to fn plus 1, or fn plus 1 is less than or equal to fn for all n. That means fn plus 1 of x is less than or equal to fn of x for all x in the domain. Okay. And once it is decreasing, you can talk about the limit. The limit may be minus infinity, doesn't matter. And let the limit is fx. Fx is equal to limit n tending to infinity fn x. The question is, then the question is, whether integral and limit you can interchange. Integral f dm is equal to limit n tending to infinity integral fn dm. Can we replace the hypothesis of monotonically increasing with decreasing in Lebesgue monotone convergence theorem, or its weaker version? Now we have the weaker version because fn plus 1 is less than or equal to fn for all x. Okay, and the answer is no. So I have to give one counter example. Okay. The standard counter example is as follows. You consider fn from R to 0 infinity defined as follows. Fn is equal to characteristic function defined on the interval n infinity, indicator function, or maybe you can include infinity so that the function will be real valued. Okay, then fn's are non-negative. Then fn's are non-negative, real value, because values that can take is only 1 and 0. Fn's are non-negative, real valued functions. Are they measurable?
Yes, sir.
Because it is characteristic function on an interval, and intervals are measurable. Okay, real valued measurable functions. Okay. Now question is whether it is monotonically decreasing. Okay, you compare fn and fn plus 1. Remember n is here, then n plus 1 is a natural number greater than it. Okay. And what will be fn of x? It will be chi n infinity, and fn plus 1 is chi n plus 1 infinity. Okay. So do you see that? Then I think I should not spend more time there. Also fn is decreasing, monotonically decreasing. Do you see it?
Yes.
Yeah. Once it is decreasing, you can talk about its limit. Okay. So let fn converges to f. What is that f? I don't know. Let us find out. We claim that f is identically 0. The limit function is 0 function. Okay, that is not hard to see. Let x is in R. I have to prove that f of x is 0. Okay. Once x is a real number, there exists an n0 in n such that x is less than n0. Archimedean property. Every real number, there set of natural number is not bounded above. Is that I am using? No. Yeah, some way or the other, for every I am using Archimedean property. Every real number, there exists a natural number greater than any real number. That's what I am using. Okay, so that implies characteristic function defined on n0 0 of x. What will be that? X is less than n0. Here you have n0, and here you have x. Now you are talking about characteristic function defined on the interval n0 infinity, but x is not in n0 infinity. Therefore, this characteristic function will be 0. Okay, and that will imply characteristic function on n infinity x is 0 for all n greater than or equal to n naught. Is that okay?
Yes, sir.
And that
Yes, sir.
implies fn of x is equal to 0 for all n greater than or equal to n naught. So for each fixed x, there is a stage n naught which may depend on x such that fn of x is 0 after that stage. Therefore, what will be the limit? Therefore, limit n tending to infinity fn of x would be equal to 0. And this is true for all x. Okay. And therefore, f is identically 0. Therefore, the given sequence of monotonically decreasing function, in fact, decreases to 0. Okay. Here, now whether the monotone convergence theorem conclusion holds or not, what is integral f dm is 0. And what is integral fn dm? Integral over r, integral over r. Yes, what is integral fn dm? Remember, fn is indicator function. That is a simple function. That is an elementary type of simple function. And therefore, what is integral of fn? Values taken times the measure. And values taken by fn are either 1 or 0. And 1 is taken in the interval n infinity. So 1 times measure of n infinity, which is infinity. So integral of fn dm is infinity for all n. Okay. Therefore, limit n tending to infinity, integral fn dm would be equal to what?
Infinity.
Infinity. We are in extended real number, so we can talk about limit to be infinity. In fact, it is diverges. But integral rf dm is 0. You cannot interchange limit and integration here. So you cannot replace the hypothesis with monotonically decreasing. Okay. So that's the bad news. But the good news is the following. Even though for a decreasing sequence, you cannot talk about limit, we can, and we cannot talk about, we cannot talk about the limit, we cannot talk about the equality. Somehow we can talk about some type of inequality. Okay, that is the limit of integral and integral of the limit will obey certain inequality. Okay, and in fact, that is the content of Fatu's lemma, the next convergence theorem. So broadly or roughly, what it tells is there is no requirement of decreasing or increasing. In fact, we don't bother whether it is increasing or decreasing. Still, we can talk about some type of convergence, but in that case, you don't have equality, you have only inequality. With that introduction, let me now state the Fatu's lemma in precise terms, theorem. I will put it as a theorem, but usually it is called Fatu's lemma. Probably the reason for calling it lemma is most of the authors approach in a different way. What we did is we proved monotone convergence theorem, and then we are going to state Fatu's lemma, and in the proof of Fatu's lemma, I will use monotone convergence theorem. But usually it is done the other way around. First, Fatu's lemma will be stated and proved, and using the proof of Fatu's lemma, monotone convergence theorem will be proved. Okay, so that's why this is called a lemma and that's called a theorem. So our approach is different. We proved monotone convergence theorem first. Okay. Anyway, both approaches are okay. Now, what is the assumption? It's a weaker assumption. Let Fn be a sequence of non-negative measurable function. That's it. It can be extended real value, doesn't matter. Non-negative measurable functions. then there is no other assumptions like increasing, decreasing or anything. There is no, once it is increasing, decreasing, etc. is not there, I cannot talk about the limit function. I'm not sure whether limit exists or not. Okay. So what the statement says is that integral lim inf fn dm is less than or equal to lim inf integral fn dm. So in the absence of monotonic increasing or decreasing assumption, we cannot talk about the equality in interchange of limit and integration. What best we can say is this: integral of lim inf is less than or equal to lim inf of integral fn. Similar statement you can do for lim supremum also with the reverse inequality. So that I am not writing. This is the standard statement in Fatou's lemma. Okay, so let us prove it. As I told, we are going to use monotone convergence theorem. But if you want to use monotone convergence theorem, you need a monotonically increasing sequence. We don't have right now, but let us see how it will be evolved. Before that, so this lemma is always confusing to me in the sense which type inequality, where is inequality, etc. Okay, and there are lots of occasions in analysis in general, not only real analysis, in analysis where we have to use Fatou's lemma to get certain things. And I am always getting confused about this equality, where to put, whether it is integral limit less than or equal to or limit integral less than or equal to. That I am getting confused. But later I started remembering like this. Let me just share with you. Integral limit is less than or equal to limit integral. That is the statement. Of course, you should keep in mind that it is not limit, it is limit infinitum here. Okay. Integral limit is less than or equal to limit integral. That is how the statement goes. And if you see, it is in lexicographic ordering, dictionary order. I less than or equal to L. If you see the first letters, it is I less than or equal to L. So you can remember like that. So IL can be treated less than or equal to LI if you remember what is dictionary order. Okay. This is how I started remembering it later. But still, in some occasions, I get confused whether it is integral limit less than or equal to limit integral or the vice versa. It should not happen to you. So you just remember that IL is less than or equal to LI. It is dictionary order. Okay. With that note, let us go for the proof. Recall. Let us start by recalling the definition of limit infimum. Recall that lim inf fn n tending to infinity of x is equal to, can somebody remind me how do you define lim inf? I consider the sequence f1x, f2x, etc. In the next stage, I consider the sequence f2x, f3x, etc. And next stage f3x, f4x, etc. and so on. So I am considering the sequence from a stage onwards. And then take infimum of this. Okay, so infimum fmx m greater than or equal to n. And now if you consider these infimums, the infimum of first set f1x, f2x, etc. and if you compare it with infimum of the second set f2x, f3x, etc. what may happen? What should happen? These infimums are increasing, right? Increasing or decreasing? Infimums are increasing. Increasing. So say take supremum. Okay. infimum of f1x, f2x, etc. will be less than or equal to infimum of f2x, f3x, etc. will be less than or equal to infimum of f3x, f4x, etc. Okay, and then take supremum. Okay, so this is the definition. This is the definition of limit infimum. Now let us consider phi n of x or phi m of x is equal to infimum m greater than or equal to n fm of x. Then, as you have already told, phi m is monotonically increasing. Monotonically increasing. And phi m's are measurable. Phi m's are measurable because fm's are measurable. And you have proved the theorem like infimum, supremum, maximum, minimum, etc. of measurable functions are measurable. So phi m's are measurable. So phi m's are measurable and they are monotonically increasing. Okay. And limit n tending to infinity phi nx. I can write limit m tending to infinity phi mx or limit n tending to infinity phi nx. Doesn't matter. Maybe I will change every m to n here onwards. Then sequence phi n is monotonically increasing and phi n's are measurable. Doesn't matter. It is dummy index. Okay. Now limit n tending to infinity phi nx is same as limit infimum fn. Do you agree? That's the definition, right? Limit of phi n is equal to limit of fn. This supremum is actually limit. Is that okay?
Yes.
So now you have phi n is monotonically increasing measurable function, non-negative, and phi nx point-wise converges. So this stage is perfect for applying what?
Monotone convergence.
Monotone convergence theorem. Okay. Now applying Lebesgue monotone convergence theorem, integral limit phi n dm is equal to phi n d. This you should not confuse. M here I used as an index. Okay, maybe I will change that m to k. Because m I am using also as a measure dm, so that will get notations will be bad then. So I will use here k. Phi kx k greater than or equal to n fkx. Okay. Now phi k is monotonically increasing, or I can say phi n is monotonically increasing. That is not an issue. Now applying Lebesgue monotone convergence theorem, integral limit phi n dm is equal to limit n tending to infinity integral phi n dm. Okay. But what is limit of phi n? It is same as limit infimum of fn. That is integral lim inf n tending to infinity fn dm is equal to limit n tending to infinity integral fn dm. Okay. Now, if you see fn's, phi n's are less than or equal to fn. Note that phi n is less than or equal to Fn. Why? See the definition of phi n. Phi n is infimum. So do you agree? Yes or no?
Yes, sir.
So integral
Yes,
phi
sir.
integral phi n is less than or equal to integral Fn. Both are monotonic and such a result we have proved. Okay. Therefore, limit n tending to infinity integral phi n dm is less than or equal to, yeah, can you complete? This is true for every n. This is true for every n. This is true for every n. Can I write this is less than or equal to limit integral Fn dm?
Yes, sir.
No, because I don't know whether limit integral Fn dm exists or not. Okay, but I can write it is limit infimum n tending to infinity integral Fn dm. I cannot write limit integral Fn because I don't know whether integral Fn has a limit. Okay, but phi n's are increasing and so on, so I know that limit infimum integral Fn exists. Okay. So this is what I have. Now substitute. Therefore integral limit we have done infimum Fn dm is equal to limit integral phi n dm, but limit integral phi n dm is less than or equal to lim inf Fn dm, and this is what the result demands. Integral of limit infimum is less than or equal to limit infimum of the integral. Okay. Please keep in mind limit of integral Fn may not exist. So that finishes Fato's lemma. Now let me supplement this Fato's lemma with remark. Remember, it is inequality, not equation. So I should say that there are examples where strict inequality happens. So you cannot expect equation every time. Okay, that's why in general statement I have put only less than or equal to. So now I will give you one example where integral lim inf is strictly less than lim inf of integral. Okay. Strict inequality can happen in Fato's lemma. You don't have to search for a new example. The example that I have given to supplement monotone convergence theorem, same thing will work. Consider Fn to be equal to chi n infinity, an element of n. Then we have seen that this Fn is decreasing, etc. And limit decreasing or not, here we are not bothered as far as the Fato's lemma is concerned. And we have seen that limit of Fn is 0 for all x in R. Okay. And what is integral Fn dm? Integral Fn dm is infinity. Okay. Therefore, limit n tending to infinity integral Fn dm is equal to infinity. Since limit is infinity, limit infimum is also infinity. Therefore, limit infimum n tending to infinity integral Fn dm will be equal to infinity. Now, integral f dm is same as integral f is limit Fn. In this case, limit Fn exists. Once limit exists, that is same as limit infimum Fn. Okay, and that is 0, we know, because f is 0. Okay, so we are getting integral limit infimum n tending to infinity Fn dm as 0, whereas limit infimum n tending to infinity integral Fn dm as plus infinity. That means in Fatou's lemma, you can have strict inequality. In fact, this example is the extreme case. One end you have 0 and the other end you have infinity. So that's why you cannot expect the equation to hold, but that is what we can say the best if you don't have the assumptions monotonic increasing. So next, let us go for another convergence theorem, namely Lebesgue dominated convergence theorem. I would say that this is the most general convergence theorem available in the Lebesgue integration theory. At least in the elementary level, this is the most general theorem. Okay. We don't need monotonically increasing and so on here. So let me state it. Let sequence Fn be a sequence of measurable function. Need not be non-negative. Measurable functions such that now the assumption you can catch from the name of the theorem, dominated convergence theorem, such that there exists an integrable function g such that already I used such that satisfying modulus of Fn of x is less than or equal to g of x. All functions in that sequence is dominated by a single integrable function, that is g. G is integrable and every function in that sequence is dominated by g, less than or equal to g. Let limit n tending to infinity Fn of x is equal to f of x. This is not automatic, this is assumption. Okay, then 1. So you have a sequence of measurable functions dominated by an integrable function, and suppose that sequence converges pointwise. Then the pointwise limit f is integrable, and further the main thing, integral and limit can be interchanged. Limit integral Fn dm is equal to integral f dm. Limit of the integral is equal to integral of the limit. Maybe everything over R. I have defined Fn as a sequence of measurable function on R. So few things that to be noted are, we don't want non-negativity assumption. We don't want monotonic increasing or decreasing, etc. Explicitly, we are not writing Fn's are integrable, but modulus of Fnx is less than or equal to g of x and g is integrable. And what is the meaning of some function is integrable? Lebesgue integrable?
Limit is less than infinity.
Limit, integral. Integral is less than infinity. Integral g is less than infinity. Does it automatically imply integral mod Fn is less than infinity?
Yes, sir.
Yes, sir.
Once integral mod Fn is less than infinity, do you get integral Fn plus and integral Fn minus are less than infinity?
Yes, sir.
And once you have integral fn plus and integral fn minus are less than infinity, do you have integral fn is less than infinity?
Yes, sir.
That means fn's are
Integrable.
integrable. So that comes from this domination. The domination asserts you that each fn is integrable. That's why you can talk about integral fn. Okay. And limit exists or not, we don't know. Suppose the pointwise limit exists, then we say that the limit function is integrable and integral of the limit is equal to limit of the integral. Okay. So now proof. Proof is not hard. I am going to employ Fartoo's lemma. We have, first let me note down the remarks that I have told. Modulus of fn of x is less than or equal to g of x and g is integrable. And g is integrable. Therefore, integral mod fn dm is less than or equal to integral g dm. Since g is integrable, integral g dm is less than infinity. Therefore, each fn is integrable. From the domination by an integrable function, integrability of each element in that sequence is automatic. Also, modulus of fn of x converges to f of x because fn of x converges to f of x. Is that okay? Further, modulus of fn of x is given to be less than or equal to g of x. Is that okay? And therefore, modulus of f of x is less than or equal to g of x. Since modulus of f and x is less than or equal to gx and the limit is this, you have. And that implies integral mod f dm is less than or equal to integral g dm. And this is finite. Therefore, integral mod f dm is finite. And that implies f is integrable. Again, it comes from the domination by an integrable function. So each fn is integrable, and if the limit exists, the limit function f is also integrable. Okay. So this part are over. Then what we want to prove is only the second main part. Limit of integral is equal to integral of the limit. As I told, I am going to apply Fartoo's lemma. Look at g plus fn. N belong to n. Now this is a sequence of non-negative measurable function. Do you agree they are non-negative? Because mod fn is less than or equal to g. Okay, so you are adding g to fn and modulus of fn at the maximum is g. So even though fn's can be negative, g plus fn cannot be negative. Do you agree?
Yes, sir.
Which is a sequence of non-negative measurable function. And that is enough to apply Fartoo's lemma. You have a sequence of non-negative measurable functions. By the Fartoo's lemma, integral limit is less than or equal to limit integral. But limit is actually limit inferior. Okay. Integral lim inf of g plus fn dm is less than or equal to lim inf integral g plus fn dm. So far so good.
Yes, sir.
And lim inf is with respect to n and g is a constant. So that will imply integral g dm plus integral lim inf n tending to infinity fn dm is less than or equal to integral g dm. Linearity you apply, linearity of the integral. Integral g plus fn you can write as integral g plus integral fn. And integral g is independent of limit infimum because limit infimum is with respect to n. So integral g dm plus lim inf n tending to infinity integral fn dm. Okay, and that implies integral g dm plus, you know that fn converges to f of x. Therefore, lim means lim sub limit, everything will be equal. So this is integral f dm. Okay, is less than or equal to integral g dm plus lim inf tends to infinity integral fn dm. Now integral g dm is finite, g is integrable. So you can cancel integral gm on both sides. That will imply integral f dm is less than or equal to limit infimum n tending to infinity integral fn dm. Okay, so this is one inequality which I may call 1. Okay, now so far so good.
Yes.
Cancellation of integral g I am allowed because integral g dm is finite. Okay, maybe I can write it. Integral g dm is less than plus infinity. And here what I used is lim infimum is same as the limit because limit exists, I know. Okay. Next, let us consider g minus fn. Next, let us consider the sequence g minus fn n in n. Do you see that this again will be non-negative?
Yes, sir.
Because mod
Uh,
fn is less than or equal to g. Okay, let us consider this clearly, and they are measurable. G minus fn greater than or equal to 0 for all n. I think I forgot to write g plus fn is measurable. That is needed because for Fathus lemma, sequence of non-negative measurable function I have written. Here also you have a non-negativeness and also you have measurability. G minus fn is measurable. So again, you are in a perfect position to apply Fathus lemma. Again, by Fathus lemma, integral lim inf of g minus fn dm is less than or equal to lim inf integral g minus fn dm. Okay. Now, as we did in the previous case, integral g dm minus integral lim inf n tending to infinity fn dm is less than or equal to integral g dm minus lim sup. I have to be careful because there is a minus sign integral fn dm. I will revisit this. That implies, let me write first, integral g dm minus integral f dm is less than or equal to integral g dm minus lim sup n tending to infinity integral fn dm. Okay. Again, integral g dm is finite and so on. So integral f dm is greater than or equal to lim sup n tending to infinity integral fn dm. Okay. Now let us go back. I think I have made a small mistake somewhere here. Yeah. So what I am using is lim sup of minus is equal to minus lim inf and vice versa. Okay. You see that I have used it correctly. So here you have lim inf g minus fn. I can write as G minus, I have to write lim sup of lim inf. Here.
Lim sup.
Lim sup, but doesn't matter. Anyway, it is finally limit because fn's are
Converging.
convergent. So I will just write limit. That's it. Again, here there is a minus sign. That's why lim inf is changed to lim sup. Okay. So you have this, which I will call as 2. Other things are self-explanatory. Now combine 1 and 2, quite easily done. So what you have to do? Integral f dm. Therefore, by 1 and 2, you have integral f dm from 1 is less than or equal to lim inf n tending to infinity integral f and dm. But you know that lim inf is always less than or equal to lim sup. Lim sup n tending to infinity integral f and dm. And lim sup by 2 is less than or equal to integral f dm. So you have equality everywhere. Therefore, lim inf n tending to infinity integral f and dm is equal to lim sup n tending to infinity integral f and dm, and all are equal to integral f dm. And that is limit of integral f and dm is equal to integral of f dm. And this proves the so-called Lebesgue dominated convergence theorem. As usual, let me supplement this convergence theorem also with a remark. This remark is to highlight that this condition is very crucial. Namely, each fn in that sequence is dominated by a single integrable function is crucial. Okay. The following example, suppose that assumption is not there, then the conclusion may not hold. Following example reveals that, I will not write the details of this, you please work it as an exercise, reveals that the importance of the assumption, the dominated assumption is important. Modulus of fnx less than or equal to g of x for all n in n, and g is integrable. Such a g exists. Without this assumption, you cannot guarantee the conclusion of Lebesgue dominated convergence theorem. So let me give you an example. Details you should work. Let fn from R to R. I define fn of x as follows. 1 by n when 0 less than x less than n, and 0 otherwise. You can note that fn converges to f. Here it is in fact converges uniformly where f is identically 0 function. Fn converges to f uniformly to 0 function. You see it, you convince yourself. Then you see that integral of fn dm over R is 1. That is easy. 1 by n times the measure of the set 0 n, which is actually an interval. Okay. So integral fn dm is 1 for all n. Therefore, limit of integral fn dm is also 1, but integral f dm is 0. So you are getting in limit of the integral is not equal to integral of the limit, even though fn's are measurable and so on. So what went wrong is that you cannot find a g, measurable integrable g, such that mod Fn is less than or equal to G. So I will just write it. Note that here Fn is not dominated. You have to convince yourself by an integrable function G. That is modulus of Fnx less than or equal to Gx and G integrable is not possible. Such a G does not exist. Try to prove it directly, but one way to see is that if such a G were existing, you would have got that integral f dm is equal to limit of integral f and dm by Lebesgue dominated convergence theorem. But that is not happening. But all other assumptions in the Lebesgue dominated convergence theorem is true. So only assumption that gets not satisfied could be this. Okay, that is one way to understand, but you have to get a direct proof for the fact that there is no G for which modulus of Fnx less than or equal to G. Are you getting my point? Yes or
Yes,
no?
Yes, sir.
So you try to prove this directly, that there is no G such that mod Fn less than or equal to G and G integrable. We know such a G does not exist by Lebesgue dominated convergence theorem, because if such a G exists, then integral of f and dm should converge to integral of f dm. But here integral of f and dm is 1 and integral of f dm is 0. Okay. Anyway, now as we remarked in monotone convergence theorem, we remark here also that the condition that we impose need to be satisfied not everywhere. It is enough to satisfy on almost everywhere. Remark. The assumptions in DCT or LDCT, dominated convergence theorem. That is how it is popularly abbreviated, monotone convergence theorem, MCT. The assumptions in LDCT may be replaced with almost everywhere. I will write what I mean by this. That is, now let me write the exact statement. Let Fn be a sequence of measurable function. I don't mind whether it is positive, negative, etc. such that there exists an integrable function G dominating Fn. Modulus of Fn of x is less than or equal to G of x almost everywhere. If Fnx converges to Fx almost everywhere, so both the domination condition and the limit point-wise limit existence condition, I changed it to almost everywhere. Okay, then the following holds. One, f is integrable. Same conclusion. And 2, integral f dm is equal to limit n tending to infinity integral f and dm. That is, integral of limit is equal to limit of the integral. So that basically what it tells is that instead of having the assumptions everywhere, it is enough to have the crucial assumptions almost everywhere. Okay. Now let me give you a argument for this, how to go for almost everywhere from everywhere. Look at, we have to consider those points at which it holds everywhere. Look at n, which is collection of all x in x such that modulus of fn of x greater than g of x. The points where it does not hold. Union, there are two things to be hold. One is the domination and one is the limit. Limit of fnx should be equal to f of x. Okay. Wherever it get violated, that I am combining. Set of all x in x or r, whatever is the domain. Okay. I will just write set of all x. That's better. Set of all x in the domain such that convergence is not there. Fnx not converge to f of x. So I combined where the domination is not there and where the convergence is not there. Is that okay?
Yes, sir.
Yes,
Now
sir.
on n complement, what you can say? On n complement. Can you say
Both hold.
modulus of fnx is less than or equal to g of x?
Yes, sir.
Can you say fnx converges to f of x?
Yes, sir.
So on n complement, both this happens. Okay. And what is measure of n?
0.
Because where this property does not hold is of measure 0, right? Because this property holds almost everywhere. So measure of n is 0. Okay. Now consider the sequence chi n complement f for fn, sorry, n greater than or equal to n. For each fn, I consider the sequence chi n complement fn. Then you can see that modulus of chi n complement fn will be less than g. That will follow from mod fn is less than g. Okay, almost everywhere. But this is true for all n. Now all x. Chi n complement fn converges to chi n complement f. Because on n complement, fn converges to f. Okay. Now you are in a situation to apply Lebesgue dominated convergence theorem. Okay. Then by Lebesgue dominated convergence theorem, we have the limit function is integrable on n complement. Chi n complement f is integrable. And you can interchange the limit. Limit n tending to infinity integral chi n complement f fn dm is equal to integral chi n complement f dm. I'm just applying the dominated convergence theorem with the assumptions that it holds for a domination and convergence holds for every x on n complement. Okay. Now note that measure of n, Lebesgue measure of n is 0. That implies integral of f dm on n is 0. That you can prove. I have proved this only for non-negative function, but once you have this result for non-negative function, you have it for f plus and f minus, and therefore you can prove that if measure of a set is 0, integral over that set of any integrable function f will be 0. Okay, and that will imply integral mod of dm is less than plus infinity, and that implies f is integrable. I am skipping the details. You can write it. It is just follows from the definition. Integral f and dm is integral over n f and dm plus integral over n complement f and dm. Okay. And on n complement f dm is 0. And therefore, this converges to integral of f and dm converges to integral over f dm. On n complement, on n or n complement, on n it will be 0, and for n complement this convergence we have. Therefore, you have integral f and dm converges to integral f dm. Okay. So what we did in MCT only, that remark similar to that. So I have omitted certain details here, but you can fill it. Okay. Now let me put another remark. A slightly more stronger conclusion you can have in dominated convergence theorem. In DCT, we can deduce that with the same assumption. Conclusion I can deduce this. Limit n tending to infinity integral mod fn minus f dm is 0. Okay. Try to do that. Maybe I can give you a hint. Hint is you have mod fn is less than or equal to g, and you have therefore mod f is less than or equal to g, and therefore mod fn minus f will be less than or equal to 2g. And now apply what we proved in DCT, you will get that mod fn minus f is integrable. And further you note that mod fn minus f converges to 0. Okay. So using these two hints, with the same assumptions in DCT, you can conclude one more thing. One conclusion is that f is integrable. Second conclusion is that limit and integral can be interchanged. And third conclusion, now I am adding limit n tending to infinity integral mod fn minus f dm is 0. Okay. So how to get the third conclusion is apply this hint. I wanted to cover one more thing, that is series version. Maybe I will state it and proof I will leave it as an exercise. Okay. Now I have a series version for dominated convergence theorem. It's not hard, so I will just put the statement and leave the proof to you. Let fn be a sequence of integrable functions that are integrable. Remember, this definition, this assumption is not there in DCT. Fn's are measurable and Fn is dominated by a G and G is integrable. So that we automatically got Fn's are integrable. Here we are assuming Fn's are integrable explicitly. And suppose that summation n is equal to 1 to infinity integral mod Fn dm is finite. Then f of x equal to summation n is equal to 1 to infinity fnx. That means you can talk about the convergence of this series summation fn almost everywhere. Exists almost everywhere, and f is integrable. If the series of integrals is convergent, then the series of the function is convergent almost everywhere. And further integral f dm is equal to summation n is equal to 1 to infinity integral f and dm. That is, what is f dm? F is summation fn. That is integral summation fn dm is equal to summation integral f and dm. You can interchange summation and integration. That is series version of Lebesgue dominated convergence theorem. And please keep in mind the assumptions. the series of integrals is convergent. The series of integrals is convergent. Then the original series will converge almost everywhere, so that you can talk about the integral of the limit function, and integral of the limit function will be equal to integral and summation can be exchanged. The integral of sum is equal to sum of the integral. Okay. I don't prove this theorem. Maybe if time permits, I will prove in the next lecture. Okay. And I will stop here. So this finishes our series of convergence theorems. Monotone convergence theorem, Fatou's lemma without any assumptions of monotonicity. What best we can say is Fatou's lemma and Lebesgue dominated convergence theorem. And then their supplement like assumption may not hold for all x. And I named one more theorem, bounded convergence theorem. I will keep it as a tutorial problem because that is a special case of dominated convergence theorem. That's a special case of dominated convergence theorem. So I will not state and prove in the lecture class bounded convergence theorem. Either you can explore yourself or I will include it in a tutorial. I will provide one more tutorial sheet and I will of course spend 2 hours for tutorial. Maybe one of the lecture class I will convert later. Okay, now 1 minute I want to take to discuss about the quiz. I would like to conduct the quiz by next week end, maybe Friday or Saturday. You discuss among yourself and tell me a time. It will be beyond the office time, that is after 6 o'clock. Or if all your classes get over by 5 o'clock, we can have from 5 to 6 or something like that. But on Friday or Saturday, discuss with your group and let me know through maybe class representative. Okay. And there were some questions like the syllabus and etc. Whether quiz can be changed to assignment? No, I can't give assignment. I will conduct a quiz. Anyway, mass copying is happening. I don't want to enter to those things. And so there is no question of assignment. I will conduct only one quiz because of time constraint. In the beginning itself, I told quiz or quizzes. I know time may not permit. Okay, so I am sticking to it. I will not go for quizzes. I will have only one quiz. Okay, and the syllabus, what I teach till the last day from the first day will be the syllabus. Okay, of course, I may give lesser weightage for already given portion and the minor. But I will not tell you what weightage I will give for that and this. So you can treat it as equal weightage. But obviously, I have to give more importance for those portions which is covered after minor. Okay. But that doesn't mean that there will not be any question from minor portion. Of course, there will be some questions. And then you were asking about, I forgot, if the class rep is here, he can. I think those are some questions that I have answered through email, but just I wanted to share with those who are present in the class.
Sir, quiz कितने marks का होगा?
Pardon?
Sir, quiz कितने marks का होगा?
Marks I can fix on that day, but the weightage I have already told. See the first lecture, the weightage I have already fixed. I will stick to it. Minor, quiz and major, the weightage that I have told I will fix. I think it is 30, 20 and 50. 30 for minor, 50 for major and 20 for quiz bar quizzes. That was the thing that we decided on in the first class. I will stick to it. Okay. But whether I will conduct the quiz for 10 mark, 20 mark or 30 mark doesn't matter. What important is weightage. So for weightage, if my memory serves me, it is 30, 20 and 50. You can confirm it from our first lecture. Did I answer your question?
Yes, sir. And sir, quiz online mode में होगा या
It will
offline?
be online. It will be online. Those who are present also can put online. Otherwise, it will be difficult. Okay. So everything will be online. And major as per the institute rules. Those who are onboarded should attend the exam in physical mode, offline mode. Okay. But quizzes, I think there is no institute rule, so I will conduct it online. Details I will send in the next lecture. Okay, thank you. Let me stop here.